Okay, physics fans. So we'll be looking on atomic physics. So we're talking about atomic physics. So first thing we'll be looking on is atomic structure. So we're going to look at what we call the atomic number of an element, and our symbol for atomic number is Z, and this is the number of protons in an atom. And protons are normally actually have a relative positive charge. And in an atom, the number of protons is equal to the number of electrons. So, for example, an atom of helium will actually have two protons, which is plus two, and two electrons, minus two. So, atoms are normally neutral, they have no net charge. Neutrons now are actually in the nucleus of an atom, and subatomic particles which are found in the nucleus of an atom are called nucleons. And there are two subatomic particles that are found in the nucleus. These are protons and neutrons. Now we're going to look at what we call nuclear number, or the mass number. This is the number of protons and the number of neutrons. There's an equation for this. A is equal to Z plus N, where A is your mass number, Z is your atomic number, and N is your number of neutrons. So like we said earlier, we have three subatomic particles, protons, neutrons, and electrons, or in the order here, we're looking at electrons, protons, and neutrons. The symbol of an electron will be E, symbol of a proton will be P, symbol of a neutron would be N. Charge would have been a negative charge for electron, positive charge for your proton, and neutrons are neutral. In terms of location, our electrons are said to be on energy shells, and our protons and neutrons are said to be in the nucleus of the atom. In terms of how would actually represent an atom, we'll write it in the form of X, A, Z, where X will be the symbol of the atom, A would have been your atomic number, and Z would have been your proton number, or a number of neutrons. To calculate the number of neutrons, you subtract the mass number from the atomic number. Now, we've actually gone into the structure of atom, so on and so forth in chemistry. We're gonna skip that portion here, and we're gonna move on into what we call our radiation or radioactivity. So radiation was found, well, actually discovered, quote unquote, back in the 1900s. They found that they actually have different forms of radiation. These days we're gonna call them alpha, beta, and gamma rays. And some of the persons who actually initially found or discovered radiation and did experiments actually died from radiation poisoning because they did not know about the hazards behind this. Persons like Marie Curie and her husband are some of the persons who actually discovered this radiation and actually end up dying. And from their sacrifices, we learn these days that we need to protect ourselves from radiation and some of the aspects and properties of radiation. So there are three types we're looking on, are alpha particles, beta particles, and gamma rays. So let's see the nature of our particles or radiation. The first one now, alpha particle is an helium nuclei. It doesn't have any new electrons, therefore that's a positive charge. It's one of the most bulky particles there in radiation, and it is the helium nuclei. The beta particle is a high-speed electron. It has a negative charge. It is quite small compared to your helium. And the last one would have been your gamma ray. This is just high energy. So when an element gives off gamma ray, it won't lose any, well, not a lot of mass property. Now we're going to look at some properties of our alpha, beta, and gamma. Now looking on your alpha, in terms of an electric field, what happens is that the alpha will attract it to the negative terminal of the field, and your beta will be attracted to the positive terminal of the field. Your gamma would go straight through the field. Let's look at a diagram how we expect this to look like. So I went ahead and made our what would actually represent our electric field as being. So let's make a note of this so you guys can know. Gonna be electric field. So our electric field will actually have two give me a second. So field. So we'll actually have two plates, or I have a positive plate and a negative plate. Let's see what happens here with that. So we're gonna represent our alpha. So our alpha, we're gonna put that in black, and our alpha has a positive charge. Opposites attract. So when the alpha is traveling through this field, it will be attracted to our negative plate, and therefore will curve along here. Alpha. Or beta, I'm gonna give it some red, and we're not gonna call it here, and it will curve along there. Or beta we expect to curve before alpha because it's lighter. Or gamma, on the other hand, we're going to make it our green, and our gamma will go straight through unaffected. And this is one of the reasons we actually believe that, or actually use and investigate the properties of our alpha, beta, and gamma. So we'll actually say, okay, since our beta is attracted to our positive terminal, therefore it has a negative charge. Therefore, our gamma is not attracted to any of these terminals. It will have no charge. And our alpha is attracted to our negative terminal. Therefore, it has a positive charge. And that's the reason behind it. The next property we'll be looking on is our radioactive particles and how they behave inside a magnetic field. So we're going to look on, well, these will actually be deflected in opposite direction. We'll look at that later on. Now, in terms of detection of or radioactive particles, we'll use what we call a Geiger molar tube, and this is able to detect any form of these radiations. In terms of penetration power and stopping power, we found that our alpha will actually only travel a few centimeters in air, and we say that these particles will ionize easily. What does this mean? It means that the alpha will actually give up its energy easy to the air particles, therefore it won't travel that far. Or beta, on the other hand, will travel a few meters in air, and our gamma will travel several kilometers in air. Now, in terms of ionization, like we said earlier, our alpha particle will actually give up its energy quite easily, followed by our beta, followed by our gamma. In terms of ionization in a cloud chamber, inside a cloud chamber, the alpha will produce bright straight lines because it's being ionized easily. The beta will produce curly lines that are not so bright, and our gamma will actually produce some squiggly lines. So you can make a note of that. Changes inside a nuclear, change inside the nucleus due to radiation. Now we're going to look at uranium. This is our uranium. In terms of number of protons and neutrons we actually have here, we actually have 92 protons and 146 neutrons. One thing about this equation, just like how a chemical equation is balanced, we expect some balance in this equation as well. For example, if you're looking at your mass numbers, 4 plus 234 would be equal to 238. 2 plus 90 is equal to 92. So this is actually showing what happens to an element when it loses an alpha particle. And we actually call this uranium U a parent, and TH we will call that our daughter. When she actually gives off radiation, she will become a parent, and what is produced is actually called daughter. And some energy will also be given off. So that's for alpha particle. You'll actually lose a mass number of 4 and an atomic number of 2. For the beta, no, what happens is that the beta is -1 plus 7 is equal to 6, and there's no loss in your in your mass number. So 14 and 14. Gamma rays, you won't be losing anything apart from this energy here, a large amount of energy. And for our formulas for alpha decay and beta decay, you can make a note of that. Half-life. Half-life actually we're actually dealing with the time taken for half the original value to be lost. So let's look here. So if we're gonna look on the half-life of a substance, normally we would draw a graph. So gonna look like an exponential graph, or when anything decays. So you're gonna lose. So we're gonna be having time. I could actually have count rate or some sort of thing. So we're gonna call it count rate. Now, if we're gonna look at half-life, we'll look at the time taken to reach. If we're gonna start at 100, it would have been the time taken to reach 50. And we measure that time there. If you're at 50, it would have been the time taken to reach 25. So it's from here to here. If you're at 25, it would have been time taken to reach 12.5. And if you're at 12.5, it would have been a time taken to reach 6.25. And in terms of fractions, this would have been, in terms of half-life, this would have been 1 half-life, and a fraction would have been, this would have been a half. This would have been 2 half-life, fraction would have been a quarter. This would have been 3 half-lives, and fraction would have been 1/8. This would have been 4 half-life, and a fraction would have been 1/16. So now that's half-life in a nutshell. Examiner might ask you to draw a graph. The graph should be a freehand graph and it should slope in that manner. Let's go back to atomic physics. So now that's half-life. Next one is gonna be nuclear energy, and this is gonna look at one of the most popular equations there is. And E is equal to mc squared, where E is energy, m is mass, and c is the speed of light squared. So we're going to look at nuclear fission. So nuclear fission actually needs to deal with when you have a large element like uranium. That's a very large element. You bombard it with a smaller element. It will be broken down into smaller elements plus neutrons plus energy. And let's do a quick check. If we're gonna add, this is gonna be 3, this is a coefficient, times 1 give you 3, plus 80 give you 83, plus 153 will actually give you 237. If you add 57 plus 35, this will actually give you 92. All these should add up. So there's some advantages of this. You can be able to control these reactions and actually collect a large amount of energy from reactions like these. We will look at the question. So what happens is that we have two type of chemical, actually two type of, not chemical, radioactive decays actually occurring, or radioactive equations. You have the natural form where one is given of an alpha particle, and you have another form where you are actually bombarded this large particle with a neutron. Now the examiner is gonna ask you to find a few things. You'll be given a table. The table, now what happens is that you will list your masses, your atomic masses in terms of U. And U is, atoms are so small that you're gonna list them in U. 1 U is equal to 1.66 times 10 to the minus 26 kilograms. So that's gonna be a conversion ratio. So in this, you don't round off any at all. You're gonna keep all these trillion decimals. So you're given the mass of all these. First question, calculate the number of neutrons of Bi. I don't normally remember the names of these atoms here. I just use the symbols. So it's gonna be the mass number minus the atomic number. So the mass number is 212 minus 83. Therefore, you're looking at 129 neutrons there. Next one, determine the atomic number of Xe. Now, the atomic number has to deal with the numbers at the top. All the numbers at the top should be equal in terms when you look at all numbers. So you can have 1 plus 235 is equal to A, which is the unknown, plus 90 plus 3. So 236 plus 93 is equal to A. A is equal to 233 minus 93. A is equal to 143. So now that would have been your mass number of Xe. Simple enough. So now this is where the cookie crumbles. Now what happens now, we need to find the, zoom out, we need to find which of these equations will actually give off more energy. And we're going to use our equation E is equal to delta mc squared. So it's actually the change in mass is actually going to give your energy. So we're going to account for all the masses. So we have one neutron. The mass number in terms of the neutron is 1.00873. Where did I get this from? I went back up here, found the neutron, and wrote down the exact number. Plus 1 uranium, or U, that was equal to 235.04393. Where did I get that from there? I went up here and I had that number there, put it from the table. So that's on one part of the equation. I bracket those minus the ones from the other part of the equation. Xe, we know where I got that from the table, wrote the exact number from the table, plus Sr, found the mass there, and I have 3 neutrons on this side, so I'll multiply this by 3. I went ahead and multiplied this by 3 before I did anything else. I don't want any mistakes, so I went here and then I subtract these two from each other, and I end up with 0.1844 U. Now I need to convert from U to kilograms, because kilograms is the SI unit of mass. I would multiply that number by 1.66 times 10 to the negative 26, which will be given in your examination. You don't need to remember this conversion ratio. And I end up with a mass of 3.06104 times 10 to the minus 7 kilograms. I don't do any rounding off. I then plug this back in the equation. This was the change in mass I just calculated. This will be the speed of light that's not changed, squared, and then I found out that I end up with a energy of 2.75 times 10 to the negative 10 joules. So now that would have been for your artificial. Now I want you guys, what you guys could do is to go ahead and work out the energy release by this equation. All the information is there given to you. So we'll be looking on some examination questions for that in our next video.